Some of the earliest hydrological features are called canals. These underground tunnels are associated with mountains and their ability to store water. In fact, today, mountains are still considered the water towers of the world. However, climate change is affecting the hydrology of the high mountain regions. The impact of deglaciation on mountain hydrogeology has not received much attention in the scientific community until recently. Here, we investigate how glacier melt affects mountain groundwater flow processes and how this will in turn affect alpine human and ecological communities in the future. The big questions I set out to answer in my master's research were: where is groundwater stored in the mountain? And what are the factors affecting the preservation of glacier meltwater? These will provide more information about how the loss of glacier ice volume in alpine regions will impact groundwater availability, ecosystem integrity, and sustainable water management practices as we approach an ice-free future.
Hello, my name is Ayobami Oluwadunsin Oladapo, a PhD student in hydrogeology in the Department of Earth, Atmospheric and Planetary Science at Purdue University. In this video, I'll take you on a journey through my research at Glacier National Park, Montana. My work explores how glacial meltwater affects mountain groundwater systems and the critical implications of this loss of ice due to climate change. I'll share insight into my findings, the significance of these changes to ecosystems and water resources, and why understanding these processes is essential for our future.
Alpine glaciers are sensitive to changes in climate. They grow during periods of global cooling and they melt in response to global warming. Recent work indicates that glacial meltwater is an important source of groundwater recharge. Once the glaciers are gone, that source of recharge is gone too, and we do not know how that loss of ice will affect the hydrogeology of the system. So the larger goal of this project was to understand how glacial retreats will affect the mountain groundwater systems. I set out to answer several important questions. First, is recharge from glacial meltwater important to groundwater flow across spatial scales, or is it localized to aquifers near the glaciers? To answer this question, I needed to know what geologic units host groundwater flow paths and what factors control groundwater flow and flow path connectivity from high elevations near the glacier to lower elevations in Glacier National Park, Montana. Second, how are isotopic fingerprints of glacial meltwater preserved in mountain block aquifers? What does the isotopic fingerprint of subglacial flow tell us about melting and meltwater processes and mixing processes? Is the preservation of the isotopic fingerprints of glacial meltwater affected by aspect controls on ice preservation? Aspect is defined as the compass direction that the glacier or mountain slope faces. Jordan Miller, the PhD student who started this project before my arrival at Purdue, used stable isotopes of water combined with microbiological markers to determine how much groundwater recharge comes from glacial meltwater. Recharge is how aquifers are replenished. This is water that infiltrates the soil and percolates the water table in the mountain aquifer. She collected water samples from springs located across elevations and used an isotopic model to calculate how much recharge comes from glacial meltwater, snow, and rain. She was able to show that many of these mountain springs do, in fact, have a strong glacial component, and that springs that depend on recharge from glacial meltwater also have unique microbiological communities. So, glacial meltwater appeared to be an important source of water across spatial scales. However, we still did not know what factors affected the preservation of the isotopic fingerprint of glacial meltwater, and we did not know how geology affects groundwater flow through the mountain block itself. We further analyzed the samples for a suite of environmental isotopes and geochemical tracers to address my own science questions. From my geological and geochemical analysis, we see that the geologic units supporting groundwater flow to springs in Glacier National Park are the Helena Formation and lower portions of the Snow Slip Formation, where carbonate rocks are present at high elevations. Springs at mid to low elevations are supported by groundwater flow from younger bedrock units and alluvium. We find evidence that groundwater is flowing along fractured and metamorphosed surfaces on the Dairat Sill intruded in the Helena Formation. Deep groundwater circulation is limited by the argillite rocks of the Grinnell and Apeconi formations, which are lower in the strat column. These units likely limit deep vertical flow in the mountain range. The diorite sill and the metamorphosed surfaces in the Helena Formation are fractured. Thus, there may be connectivity through secondary porosity. This means that groundwater flow is likely focused above the argillitic units, and there's limited connection between glacially recharged groundwater and low elevation streams. In other words, groundwater storage within the syncline of Glacier National Park may be limited to high elevation rock units. Aspects plays an important role in the preservation of glacier ice. North-facing slopes in the northern hemisphere and south-facing slopes in the southern hemisphere should preferentially preserve glacier ice. If ice preservation is aspect-dependent, then those sample slopes preferentially receive and preserve isotopic fingerprints of recharge from glacial meltwater for an extended period of time. This is a generalized model on how we think ice is preferentially preserved in the mountains. In the northern hemisphere, we expect to see preferential preservation of the isotopic signal based on aspects, meaning the north-facing slopes will retain or preserve glacier ice the longest. We would expect that these slopes of the mountains would retain their isotopic or geochemical signature that is similar to the ice or similar to the meltwater. However, we see the south-facing slopes preserving the meltwater signal rather than the north-facing slopes at Glacier National Park. Aspect is difficult to assess in Glacier National Park due to hydrostratigraphy. Structural and stratigraphic controls on groundwater flow and circulation override aspect controls. Simply put, some of the stratigraphic layers dip to the south and southeast. Thus, more springs emerge on the south-facing slopes, and the isotopic fingerprint of glacial meltwater is more apparent on south-facing slopes due to groundwater flowing down deep.
Glacial retreat is a global threat. The hydrogeology and hydrology of our high mountain regions are changing rapidly. This is creating sustainability problems for the Alpine communities. These communities depend on surface runoff and groundwater recharge from glacial meltwater for survival. Accelerated retreat of these glaciers is affecting the livelihood of these communities. During periods of low rainfall and seasonal snow, groundwater discharge to rivers, springs, and streams is vital to the ecological integrity of alpine aquatic ecosystems. Glacial meltwater support the recharge to these aquifers that in turn buffers or moderates impact of climate change on these hydrological systems. Alpine regions are biodiverse, so the worldwide retreat of mountain glaciers is a threat to alpine biodiversity. At the end of my research at Glacier National Park, Montana, one thing became crystal clear. Glaciers are retreating faster than we have been generating knowledge about their importance to mountain groundwater systems. Hopefully, with this new interest in alpine glaciers and mountain groundwater, we can provide the much-needed data to support future water management and adaptability strategies.